А где эти переключать? Переключать чем?
Да.
Там. О, все. Добрый день, уважаемые участники форума по практическим.
I welcome all of you. I'm Yuri Огородников from Omsk Technical University, where I'm a postdoc. I will be speaking RSA algorithm attacks. RSA is the encryption algorithm. SAT is a very important topic. I will be using this acronym SAT, SAT in the future. RSA algorithm is the algorithm which was developed in the last century. It became popular quite quickly. The analysts wanted to decrypt that. Let us take a look at sending an M message. The message is sent and the open key is used here, so it sends to AISA. It takes the closed D key and decrypts it. Here is our cryptanalyst, which intercepts this message and tries to recover it, tries to recover the secret key. What are the methods used here? You can attack RSA, factorization, open exponent, and you can attack through the use of the quantum computer. Factorization is the first group. RSA is based upon this algorithm. Digit number is the most effective approach. We're able to go up to 868 bits, but it had some challenges. First of all, it's the heuristic approach. We did something, and we don't know how it works, but it does work. And you need to find simple digits there. The second one is the Pollard method. That's where we use simple numbers. That's the heuristic approach, and it's not used at all times. The second group of methods is based upon the exponent, small exponent. RSA is quite slow as compared to ordinary symmetric encryption protocols. It's used to encrypt the key, where the main data is used. The encryption speed, RSA encryption speed increases. But in this case we have additional vulnerabilities, like the hasted attack. When a few aliases get a message, an open key message, the hacker collects them and can reveal this message. The next thing is the exponent attack. We know that if we are aware up to 1/4, at least 1/4 of the bits of the secret key, we can recover this key if the exponent is small. The third group is the RSA attack. This first attack is the time-related attack. Different operations require different times. If it's a black key, encryption is done a certain number of times. You need to fix a certain number. And here we measure the analysis of violations, where the hacker sends a signal which is dedicated to create a crash of a program. And the encryption is done in a wrong way. Wrong data is used. By using this data, the hacker can do something. The fourth method is the fault analysis. For example, a message is sent and a modified message is used instead. If the server decrypts it in the proper way, they see and check what has been sent there and intercepted. If it was not capable of deciphering, it sends yet another message. And by sending a new message each and every time, the hacker can figure out the actual message. But they will require way too many messages for that. And the quantum computer is the fourth way. Quantum computer is using it in a very simple way, but there seems to be just one problem. It's not done yet. All these advantages, all of them have advantages, and we develop our own one about factorization. The factorized n number as far as you can see here, p and q bits are the numbers related to the factorized number, and here p is the solution, n with the s index. What's our idea? We do it on our own, but not completely, but before it's reservable or through a number of iterations. There is no fast algorithm to it. So we have an approximate solution. We benchmark it against the template and have a statistics of every bit. Then we set the initial SAT solution and we clarify it through a number of rounds. And we have a probability algorithm. To improve efficiency, we'll be resolving it through a number of methods, through linear equations, through functions which can be modified in three ways. The rounding, the variables, etc. For each method we have a series of tests and we get statistics with the definition of every bit. Then all of these methods are combined. A multiple number of bits are split into 4 clusters, and each cluster is using exactly the same algorithm, which is best suited here, and is defining the cluster with best frequency. So here we have the testing results in percent. The bits allocation, they're evenly spread. So we don't have it like 1, 2, 3% available. Each algorithm is important. This algorithm can be used in the distributed fashion. For example, you have a data center with a few servers using different algorithms. I'm showing you the testing results. The first column is the number of the bits identified. The number is reducing, but it's not critical. Here you see how we compare it with the famous algorithms. We also benchmarked it with the analogs. With the small sizes, our algorithm is slow. But then we start to win just because of the fast process. And you can see that the lower curve is our algorithm. Let's speak about the practical part. We have the frequencies, and that's how we can do some approximation. Set and J set, which we can use here in combination with our approach. We run it with a few rounds, 1,000 rounds, and we either get the answer or not. The horizontal strip shows here that it has not been found over 1,000 rounds. It's not 500, it's not 468, but our algorithm is still scalable. So we can attach additional modules here. We can also use it for discrete algorithms. A lot of tasks are done through it, not only factorization but other encryption problems. Our algorithm is quite fast and works faster than its competitors. By adding new modules to our solution, we'll be increasing frequencies and be factorizing the numbers. I'm done. Thank you very much for listening. Your questions, please.
Юрий, у меня вопрос к вам.
Yuri, here, the time is a very subjective factor. What about the algorithmic and rhythmical challenge, which is important here? Can you tell us the value? It's a probability algorithm. It gives us some answer, but with some mistake. For example, in the linear equations, it works with a 10m. So it uses the standard dependency. Yes, thank you. You pointed out that it's in percent. In percent, these algorithms are suitable, more suitable. But what about the allocation? So we can see the total number. I was talking about your pie chart. Could you repeat your question, please? So that's the percentage. The bits defined by this or that algorithm. No, that's the allocation of the bits by clusters. 34% of bits are defined by the first algorithm. What about the allocation and allocations? Some of them are fixed, some of them are not. But I don't really understand your question. You have a number of bits here, and these bits, can the allocation of the bit be related to the allocation on the pie chart? Yes, you can with some of them, but some of them unstable. If that's all about factorization, bit number 1 and bit p and bit t plus iq, they are reliable. All the other ones are variable. Some of them are defined by one algorithm, some not. Use a standard solution here. Okay, I think we should